Hello dear students, let us analyze heap sort in this video. Now in the earlier video, we actually saw two formulas. First one was about height of complete binary tree. If a complete binary tree is given having 15 nodes, or rather full binary tree of 15 nodes, then the height is given as floor of, check the result written below, height of a complete binary tree with n nodes is floor of log of n to the base 2, where n are the number of nodes. And second formula we saw was given any height, remember heights were numbered from bottom level as 0 and then increases upwards. These are the heights. Then if we are given any height, for example height 1, then how many nodes, maximum nodes can be there at that height is given by ceiling of n upon 2 raised to h plus 1. Now using these two results, we will very easily analyze heap sort. Now you recall, as we learned in the earlier videos, that heap sort works in two stages. Now stage 1 of heap sort, as you all know, is we create a max heap, isn't it? Now given a complete binary tree, this is a complete binary tree, what do you do to create a max heap? Remember stage 1, we adjust value of all the parents. And you also recall that we start with the last parent. The last parent in this particular tree shown is located at 7th node, as I am again marking here, isn't it? After the 7th node, all the nodes like 8, 9, 10, 11, all these nodes are leaf nodes. So last parent is situated at 7th node. And what we have to do is adjust the value of this parent. What do you mean by that? We want max heap. That means the value of this parent, parent 7, which is right now 4, should be larger than both the children. So what do you do is this 270, which is larger, check that 270 is larger, is shifted up. So 7th node is going to store 270 and 4 comes at the bottom here. Now just check 7th node, which is parent of 14 and 15, is indeed larger than 60 and 4. But how many comparisons did you do to adjust this parent 7? Is hardly one. I hope you will understand this point. You just did one comparison, come on, because either the left child or right child will be shifted up depending on who is larger. That means the parent value, 7th value, was compared only one level down. Isn't it so? So just by using one comparison, only by using one comparison, we adjusted 7th parent. Then we came to 6th parent. Remember, stage 1 starts with last parent 7 and goes down to first parent. So 6, 5, 4, 3, 2, 1, like that it will adjust. So how many comparisons you will have to do to adjust the 6th parent? Just imagine that at 12th node, we had a value 75. And at 13th node, we had a value, let's say 76. Now you will be comparing this parent value with the largest child of the two. 76 is the largest child, but hello, this parent value 250 is already larger than its largest child, isn't it? So you will say 250 is ideally suited at 6th place. And you will say that you have fixed this 6th parent. It is now larger than both the children. But how many comparisons did you do to fix this 6th parent? 6th node? Only one. Again, only one comparison was done because there is only one level below this particular node 250. So either left child will shift up or right child or none. Similarly, for fixing this 5th node, you will need only one comparison. And for fixing this 4th node, you will need only one comparison. What I want to point out is a very important, very important observation. If you are talking about nodes at height 1, observe the height here. These four nodes, 4th, 5th, 6th, and 7th nodes, are located at height 1. Remember, height starts with 0 down and then increases upwards. So if you observe these four nodes which are located at height 1, then for fixing the value of each node in stage 1, we just needed one comparison. Isn't it so? Are you understanding? For fixing this sixth node, we needed only one comparison. For fixing this fifth node, this parent should be larger than its children, isn't it? We needed only one comparison. For every node over here, we needed only one comparison, and that is indeed the height. One is the height. So given some height, if we talk about some height number, given some height h, talk about only nodes at that height, okay? Like we were talking about nodes at height 1. So given some height, what is the total time taken? What is the total time taken to fix all these parents, all these 4, 5, 6, 7? How much time was taken? How many comparisons were taken? Yes, for fixing every node, only one comparison. That is H comparisons. H is 1 at the moment. H comparisons were taken to fix every node, isn't it? But how many nodes are there at this height? Yes, the number of nodes at this height. We learned the point number B. Maximum number of nodes at level H, that is height H, is ceiling of n by 2 raised to h plus 1, isn't it? So number of nodes at height h is n upon 2 raised to h plus 1. That means so many nodes were adjusted at that height. And for adjusting every node, we took h comparisons. Are you understanding? For one node, we took h comparisons. For another second node, we took h comparisons. For third node, we took h comparisons. But how many such nodes were there? The number of nodes at that height h were n upon 2 raised to h plus 1. This is for one particular height, isn't it? Okay, what do you do after that? Imagine we have adjusted all these parents. Just imagine we have adjusted 4, 5, 6, 4, 5, 6, and 7. We have adjusted all these parents, isn't it? Now what? Now we have to adjust the third parent, then second parent, and then first parent. Correct? I hope you are listening properly. We have adjusted first the seventh parent, then sixth, then fifth, then fourth, came back like that. And now we are going to adjust third and second parent. That means we are now working at height equal to 2. Check that at height equal to 2, there are two parents located, 2 and 3. Now you tell me how many comparisons you will require to fix the parent located at number 3. I'm pointing out this parent again, 200. Somehow we want this value to be larger than all its children. So first comparison will be done here at this level where I am marking, and the second comparison will be done at the bottom level here. So maximum two comparisons. You see the shift up can be done. Maybe 13th value is very large, it will shift up, and then this value is also very large, it will shift up. That means maximum two comparisons will be done. Similarly, for this second node 50, we want it to be larger than all its children, then maximum two comparisons will be done. What I mean to say is that at height equal to 2, if you check the height, this height, I'm talking about height equal to 2 here, there are two nodes located, isn't it? And for every node, hardly two comparisons are needed. But that 2 is nothing but height, isn't it? So again you observe, given some height, just check this, given some height h, and we are asked to talk only about nodes at that height. How many comparisons are needed to fix all the parents at that height? For every parent, we require h comparisons. Again notice, for fixing third node, we needed two comparisons. For fixing second node, we needed two comparisons. That is h. So for fixing any parent at height h, we require h comparisons. But how many such nodes are there at that height? It is n upon 2 raised to h plus 1. These many comparisons are needed to fix every node at height h. I hope you have understood this formula. And now ultimately, we have to calculate the total cost, isn't it so? Now the total cost will be the cost of adjusting the parents at every height. And what is the height of this tree? Remember, height of the tree is log of n to the base 2. So if you say that at a particular height, the cost is n upon 2 raised to h plus 1 multiplied by h, correct? This is for one particular height. But we have height 0, height 1, height 2, height 3. Then we will have to sum up the individual cost at every height where h goes from 0 to log n. I have done a bit of blunder over here. You see that I have included height equal to 0 also. But actually, at height equal to 0, no work is done. We don't fix this node, this node. These nodes are already fixed. We only start from parent nodes. But then we have taken this 0 also so that our analysis becomes easier. Anyway, we have to go for worst case, big O notation. So adding something to a big O notation is not going to hinder our final result. Anyway, so I have taken this summation from 0. Now watch this. Here n is not going to change in this formula. What is changing is h, isn't it? H is going from 0 to log n. So I can take n out, and this denominator can be written as 2 raised to h multiplied by 2, isn't it? So even that 2 is a constant. I can take it out. So this summation becomes summation of h equal to 0 to log of n. In the bracket, what remains is upon h upon 2 raised to h. And what remains outside is n by 2. Now I am going to do something which should not shock all of you. I am going to write this value is definitely less than n by 2 into summation of h equal to 0 to infinity. Check that I have replaced this log of n to the base 2 with infinity. What are we summing up? H upon 2 raised to h. Just check that. How dare I can change this log of n to infinity? Hello, we want to prove that the time taken is of the order of something, isn't it? So we want to find out the uppermost bound. So we want this function, if we call this as fn, this function is definitely less than what? So if we replace this log n with infinity, we are summing up a lot. That means we are saying that the height of the tree is not log n, it is infinity. It continues to grow, isn't it? In that case, definitely this right hand side is going to be a very large quantity as compared to left hand side. I hope you are understanding. Now, the one more reason behind doing this is that this written summation of h goes from 0 to infinity, this portion, h upon 2 raised to h, is a harmonic progression. And it has been proved by mathematicians that this amounts to 2. Value of this is 2. Oh, great. Just see, the value of this is 2. I'm not proving this. This is beyond the scope. But if we have summation of x goes from 0 to infinity, x upon 2 raised to x, this is a harmonic progression, and this amounts always to 2. This is a famous mathematical result. So what you see is the left hand side function over here. This left hand side function over here, let's call this as fn, is less than n by 2 into 2. That is n. And if any function is less than other function, we can say fn is big O of n, isn't it? What that means is that the stage 1 of heap sort works in the order of n, big O of n. You see, it is so accidental. Many students initially feel that the first stage 1 of heap sort, is going to work in n log n. But the tightest bound of the stage 1 of heap sort is big O of n. Just to summarize, before it irritates you, talk about some height. How many nodes are there at that height? N upon, where n are the number of nodes. Remember, number of nodes here are 15, total number of nodes. But maximum nodes at a given height h is n upon 2 raised to h plus 1. And you are fixing all these nodes in stage 1. You want them to be greater than their children. But then how many comparisons you will do at this height? Just one. Because look at the level below this. You have only one level, isn't it? So in general, at any given height, you will do h comparisons for every node, isn't it? Located at that height. And how many such levels are there? How many such levels? It is height of the tree. Number of, what is the height? Log n. So we vary h from 0 to log of n to the base 2. And this we got is less than big O of n. Just as we got harmonic progression and all that. So this is analysis of stage 1. Now stage 2, nothing. Now it's very easy. Now, after converting this entire binary tree into max heap, what we do is we know that the topmost node, is the largest. We always know. Let's see one of the max heap we got earlier. I think we got max heap. Yes. Let's see. This was the max heap we got. See, every value of the parent is larger than its children, isn't it? So what we did then is that we swapped this first element with the last element. So this last element was 250 and eighth element was out. So size of this heap was reduced to 7. Initially it was 8 and the first element was 50, isn't it? First element was 50. Okay, that is what is shown below in the diagram. First node was now storing this value 50, isn't it? But we wanted this entire tree in the form of max heap again. So what we did not adjust any parents except the first parent. We adjusted only the first parent, isn't it? Now you tell me, to adjust this first parent, how many maximum comparisons will be needed? Yes, you are correct. Two comparisons. Are you understanding? Isn't it? Two comparisons, but that is nothing but height of the tree. And height of the tree is log n to the base 2. Yes, 7 nodes here. That is log of 7 to the base 2. Remember, we are taking the log of 7 to the base 2, and log of 7 to the base 2 is going to be 2 point something, and we always take floor of this. That's going to be 2. So tell me, to adjust the first parent, how many comparisons you will need? Log n. Isn't it so? But after doing all this work, we saw that 225 got lifted up, correct? Then 150 got picked up and 50 got settled over here. Now what happened is this 225 was the largest. This 225 was swapped with the last value again. So we got 225 and 250 sorted and then 4 on top. But then rest of the heap, check this, was to be converted into max heap. So what we did to convert it into max heap, we did not adjust all the parents. We adjusted only first parent because all other parents were already greater than their children. But then how many comparisons you will need to fix this parent in this tree? Yes, again two comparisons, isn't it? That is nothing but log n. This is the height of the tree. And we again got 200 on top. That's the largest. We keep doing this till this entire array gets sorted. That means at the moment we saw 1 and 7 were exchanged. Next time 1 and 6 will be exchanged. Next time 1 and 5. Next time 1 and 4. Then 1 and 3. And finally 1 and 2. And then we will know that the array is sorted. So each time we adjusted the value of the first parent, it took log of n to the base 2 comparisons. And total there are n elements in the array, isn't it? N elements. And for fixing each element, we require log of n to the base 2 comparisons. So how many total comparisons are needed? N multiplied by log of n to the base 2. This is the analysis of stage 2. Come again, in stage 2, we fix only first parent. And to fix the first parent properly, number of comparisons needed is equal to height of the tree, and height of the tree is log of n to the base 2. And we keep doing this by exchanging every time first element with the current last element. So number of elements are n, and for each element log of n to the base 2 comparisons are needed. So total comparisons needed in stage 2 is n log n to the base 2. So coming back finally to our analysis, stage 1, observe, we already took this analysis. Stage 1 is big O of n, and then follows stage 2. Stage 2 is n log n. So the total time taken will be big O of n plus big O of n log n. And you know, as we are talking about O notation, we will take only the largest term, and n log n is larger than n. So we will say analysis of heap sort is big O of n log n to the base 2. In fact, in summary, I can say that analysis of heap sort is analysis of stage 2. We give more respect to stage 2 because it is going to take more time, and we borrow this as our answer, and we just disrespect a bit the stage 1 analysis where we build the entire heap, entire max heap by adjusting all the parents, and that had analysis as big O of n. But it is disrespectful for this stage 1. We have ignored this because this is n raised to 1, and here we have n raised to 1 into log n. So we will take big O of n log n to the base 2. I hope you have understood analysis of heap sort. It has been a long topic for us, but I promise that you will get many questions in many GATE papers about heap sort where you will be comfortable to attempt them. Thank you.